In this lesson, we'll explore the object-oriented paradigm of inheritance. We'll show how we classify new blocks using inheritance, and we'll identify attributes and behaviors that belong in a parent class. We'll also identify the attributes that belong in child classes, and we'll use the block game as our example. We'll use an object hierarchy to avoid writing more code and make expansion of our game possible. It's worth noting that we're not going to discuss everything about inheritance. We'll just look at how we implemented our blocks in the block game using inheritance. Inheritance is the relationship between a parent class and a child class. Now, you can have many child classes, and they can all extend or inherit from a single parent class. The child class inherits all of the data and behavior of that parent class. You can think of it as an instance of the parent class that adds some specialization to it. You can always treat the child class like the parent class because of that, but the same isn't true for the parent class. All parent classes don't implement everything that all the child classes implement. Let's look at the example we used in the block game. We made the BP base block, and it's the parent class of all blocks in the game. The BP dirt block, the grass block, and the stone block are all children of that BP base block. Instances of those three child classes implement the getAttach location function, and the reason they do this is because it's written in the parent class. So we can add special abilities to the child classes. For instance, we can make it so that the dirt block starts to grow grass when it sits uncovered for a period of time. We would only implement that in the dirt block and not the stone block. So therefore, the dirt block is a special child class of the parent class, and the stone block is too. It looks different, and it may have some behaviors of its own. But both of them implement that getAttach location function that's in the parent class. So even with the special abilities that you add to those child classes, you can treat them all as BP base blocks. I made a couple of specialty blocks to use in the block game so we can show how the parent-child class is implemented. The BP base block is on top, and the child classes are on the bottom. The arrow blocks I made just have arrows in them for the static mesh that point up to the parent class. So the dirt block, the grass block, and the stone block are all children of the BP base block. You can consider that they're siblings of one another because they share that parent, but they implement their own materials and their own behavior if we were to add some specialized behavior to them. With a parent variable reference, we can call functions or get data that only exist in the child. But to do that, we have to cast that reference to the child first. We do this in the block game. There's examples of this, and we'll look at them in just a second. We get the HUD from the parent controller, and then we cast it to an HBP crosshair, our specialized crosshair. So the HUD is the parent class that the HBP crosshair inherited from, and we need that HBP crosshair because we have to get the data from it. When we get the block that was clicked on, we cast it to a BP base block, even though it might be one of the many different types of child blocks that are available. Let's look at the code. In the begin play event, we get the player controller, and then we get the HUD from the player controller. This returns a HUD class. We have to cast that to the HBP crosshair, and we know it's the HBP crosshair because we set that in our game mode as the HUD that was going to be used for our game. Notice that there's the possibility that the cast may fail. Now we, again, know that it's going to be the HBP crosshair, so we're pretty certain that we're going to get a valid HBP crosshair reference from that cast. But if you don't know for sure that you're going to get that child class, you have to take care of the case where the cast might fail. Once it's casted to that type, we can use that reference as the type that we casted to. And in our case, we just capture it as a variable for use later. Here's a case where we deal with the fact that we might not get one of our blocks back in a cast. So in the get clicked on block function, we grab the hit actor, the thing that was hit by the line trace, and we try to cast it to a BP base block. If it succeeds, we return the BP base block so that the code that needs to ask it where to attach the next block can call that function on the BP base block. In the event that it fails, we have the hit success value set to false so that we know that the hit block isn't valid and it's not a BP base block. By checking that we connected with or our line trace connected with an actual BP base block, we can write code that deals with the situation where it's successful and not successful. Another place where we use inheritance is we have the all blocks array. That's an array reference to BP base blocks. With the exception of the 0th element, which we put a BP base block in, all of the classes listed are children of that BP base block. Since the child classes have the full power of blueprints, they can implement completely customizable behavior. Let's look at the example of the BP random flower block. The BP random flower block changes the static mesh in the construction script. None of the other blocks we've built up to now do that. So let's look at it. The block mesh is set to the SM underscore flower daisy01. Now, if we did nothing, we would always get that flower block or that static mesh every time we made one of these. But in the construction script, we implemented some specialized behavior. We've got a random integer from 0 to 2 being taken, and then option 0 returns the daisy01, option 1 returns the daisy02, and option 2 returns the daisy03. And then we change the block mesh in the construction script. The result of this is when we play the game, every time we put down a block of type random flower block, we'll get a random flower. Let's look at that in the game. I'll scroll to the random flower block, and when I click and add it, see that we get a random flower each time. Now you could get the same flower several times in a row like I did there, or you can get a different flower. Now notice that this is a BP base block. When we click on it, it tells us the next location to add, and that code works. So we can treat it like any other block, and we can remove them by right-clicking or running the remove block action. And by using the power of inheritance, we've created that specialized block, the random flower block. Let's look at the all blocks array again. The all blocks array has class references to BP base blocks. The 0th element is a BP base block, but all of the child classes are children of the BP base block. When implementing inheritance in your games, take your time to carefully analyze the relationship of the actors in the game. Sometimes an object hierarchy makes sense, and sometimes it doesn't. Sometimes you can implement the differences between child classes with data. For example, we could have used a way to change the material of the BP base block so that the material changes. But by implementing it the way we did, we allowed for having specialized blocks as the child classes, for instance, the random flower. You can add all kinds of interesting behaviors to the child classes in this game. I was experimenting with blocks that blew up after 5 seconds and took out blocks around them. I had blocks that had lights, blocks that had fire, and just had fun creating all kinds of different blocks just to experiment with and try them out and see what it looked like. And by using this parent-child relationship, it made it very easy to do that. In this lesson, we discussed classifying new blocks using inheritance, and we identified some attributes and behaviors that belong in the parent class, for instance, the get actor location and the static mesh that represents the block. We identified attributes that belong in the child classes. For instance, we could change the static mesh, or we could add things like fire or some ability to have a TNT type block or an explosive type block. We demonstrated the object hierarchy that avoided writing more code and made expansion of our game possible.